and we can start the third day of SRDS. Thank you everybody for being here. Thank you everybody that is watching from the YouTube link. We are very lucky to have Professor Nitin Vaidya with us, giving the third keynote of SRDS titled Security and Privacy for Distributed Optimizations and Learning. I have only 1 hour slots, which means I cannot tell you everything and every accomplishment that Nitin has done so far. I'll go quick and say Nitin is the chair, the lead chair of the CS department in Georgetown. He got his PhD from UMass Amherst, and he was a professor before at University of Illinois at Urbana-Champaign. He's an IEEE fellow, chair of the steering committee of policy for a while, and editor-in-chief for transactional mobile computing, as you probably know. We are all looking forward for your keynote speech, and the floor is yours. We will make sure to read questions over Zoom or Slack as they come to you, Nadine, so you don't have to worry about that.
Okay, so I'll try to share my slides. Hopefully it works. Okay, I think you can see me.
Yes, awesome.
Okay.
Thank you.
Sure. Well, thanks for inviting me. So this is like we have been told, it's less than 1 hour, and given the short time, I won't give you any theorems or proofs. My main goal is to just communicate to you the problems we are working on and tell you a little bit about the solutions and hopefully some intuition behind what's going on. But there is in fact a 5-6 hour tutorial that I have recorded that's available via YouTube that you can watch later if you find this talk somewhat interesting. So the talk is about distributed optimization and learning, but privacy and security issues for those two problems. So what is distributed optimization? Here is an example problem. This is a map of Washington, DC, Georgetown area. Let's say 3 of us want to meet for dinner tonight, and those are the 3 locations where we begin. And to choose a location, we can do it in many different ways, but the way that is relevant for this particular talk is that we're going to define a cost function. These 3 people are numbered 1, 2, and 3, and X is the location where we meet. And depending on where we meet, I have a particular cost of getting there. The cost could be money, it could be time, it could be the energy resource, if it is a robot. And so let's say F1 of X is my cost function of getting to location X. I'm agent number 1, and you are agent number 2. Your cost function is F2 of X, and so on. And a reasonable way to pick the location would be to minimize the aggregate cost. Minimize sigma fi of X over all I. Summation is over all agents I. And if you haven't seen argmin before, it just denotes the argument, the X, that minimizes sigma of fi of X. Now, this is a particular goal. You might, in a different context, you may have a different optimization goal, but this is the kind of optimization goal we are going to deal with today. These kinds of cost functions, the sigma fi X, appear in all sorts of settings, including distributed machine learning. So you have a situation where now you have multiple agents again. Each of them has its own data set. The agent may be a hospital, for example, or it could be our cell phones, right? There are millions of cell phones that represent millions of agents. And you want to train a network, perhaps a neural network, using the data that resides in these different agents. One way to do that is to bring the data to one location and then train the machine. On the other hand, you could try to do this distributedly, where the data resides where it is, but the agents collaborate somehow to train the neural network, support vector machine, whatever algorithm, whatever machine you want to train. But the core collaboration is required because the data happens to be distributed. And in case of machine learning, the cost function, F1 of X, is the so-called loss corresponding to data at agent number 1. F2 of X is the loss corresponding to data at agent number 2. Loss achieved at a particular parameter vector X, let's say for a neural network. And to train the neural network, we minimize the global loss over all the agents. So again, you have the cost function sigma fi of X. So this particular cost function, like I said, has many, many applications. People have been studying this for something like 40 years, as in there have been distributed algorithms proposed for solving this problem for close to 40 years. Just to give some background for those of you who don't recall high school calculus anymore, this is how we minimize a cost function, or particularly a convex cost function. In this case, the argument x is two-dimensional. So imagine that you're on a plane and the vertical axis is the cost, and you want to meet somewhere on a plane, kind of like going for dinner. And the optimization algorithm, this is a centralized algorithm. We start with an initial guess of the optima. So let's call it x0. And obviously that's not the minimum, but we will now take a step so that the cost function is hopefully reduced when we take the step going from x0 to x1. When we get to x1, we take another step to go to x2 and to x3. And that step is represented by this iteration, the so-called gradient method. So if you already have estimate xk, which initially is x0, k being the time index, to get xk plus 1, we take xk and then take a step. The step is taken in the opposite direction of the gradient or the derivative if you're dealing with scalar arguments, and multiply by this so-called lambda, which is a step size. In general, the step size lambda can depend on k, and it often does depend on k. I just simplified the expression here. But this gradient is the important part in taking this step. And what you observe in this gradient is that because my cost function fx, which is a global cost, is summation of fi(x), the gradient of fx is also the summation of gradient of fi at the current estimate xk. Now, finding the summation is slightly challenging in our setting because each agent only knows its own cost function. So the cost function of agent I is private to agent I. And so they need to somehow do this computation of sigma fi of x. And this is where one might use distributed algorithms. They don't have to be complicated, but they can be fairly complicated depending on the type of network you're dealing with. So over the years, these algorithms have been studied, or these kinds of distributed optimizations have been studied in two settings that look quite different. On the left here, the blue nodes, this is a peer-to-peer network. It's an arbitrary graph that happens to be connected in this case. And each agent in this setting can only talk to his adjacent nodes, the near neighbors. And the algorithms proposed for this are very local in that the agents don't even need to actually know the network topology, and yet they can solve this distributed optimization problem collaboratively. In recent years, because of the interest in machine learning, in practical settings, this architecture on the right-hand side has come into use. It's a server-based architecture, makes life much easier if you have a server helping all these agents to do this collaboration. The work I'm presenting today meaning the problem of fault security and privacy, or fault tolerance and privacy, has been investigated in both settings. I'm going to focus on the server-based architectures because it makes life easier. And in fact, for fault tolerance, this peer-to-peer architecture, the number of results is still quite limited. So like I said, if you could find results in both settings, but I'm not going to talk about the peer-to-peer setting at all today. Those algorithms are actually much more interesting, honestly, but it's only have 40 minutes to talk about it. So here is the server architecture. It's very simple, at least in the very basic case. So these are the agents. There are 3 agents, let's say 1, 2, and 3. Each agent I knows its own cost function fi of x, and the server is going to help them compute the argument that minimizes sigma fi of x. So the server maintains the estimate of the minimum. Initially, it would be x0, the initial guess made by the server. And then the server sends its current estimate, xk, to all the agents. And those agents, having received the estimate from the server, send back to the server the gradient of their own cost function at that estimate. Now, when the agents send the gradient back, it could be a message, or if you're working in a shared memory architecture, it could be a write operation into a shared memory register. But somehow server receives these gradients from the agents, and then the server does the obvious thing. It just adds up all the gradients and then takes a step. So this algorithm is kind of trivial and silly because we are not really doing very much here other than simulating a centralized algorithm. And in fact, nobody uses this algorithm in practice because it is A synchronous algorithm, it tends to be expensive because the server has to wait to receive the gradient from all the agents before it can take steps. So in practice, there are many variations on this simple structure that have been used. People often use stochastic optimization, particularly in machine learning, because those data sets have some redundancy. Stochastic optimization can achieve some efficiencies. The algorithms tend to be asynchronous in practice, and there are many other optimizations that have been proposed. We will not deal with any of this today. However, I'll point out that there exist fault-tolerant algorithms that are stochastic and asynchronous. So what are the challenges? I've been talking about saying privacy and security. And so those are the two challenges we are dealing with in our work. I put the word privacy in the title, security in the title, because people just seem to like that, but I really prefer to use fault tolerance for it, the jargon fault tolerance for it. And in particular, we do Byzantine fault tolerance. So here is the problem. You have, again, a bunch of agents. They have their own cost function. And if one of the agents, or more than one, is compromised or faulty, it could misbehave. And in the algorithm we just saw, it could misbehave by sending bogus information to the server. And if you recall the algorithm, server receives the gradients from the agents and adds them up. But if one of the gradients is bogus, then clearly that's going to tamper with the computation the server is trying to do. So question at the highest level is, how do you perform this distributed optimization if some of the agents may inject bogus information into the computation? So those of you working on Byzantine fault tolerance, this should seem very familiar, the question itself. But the question wasn't asked previously in the context of optimization before we started working on it. The dual problem is privacy. Now, in this setting, we don't have agents tampering with anything, but perhaps the agents want to protect the privacy of their own cost functions, and therefore, in turn, the privacy of their own data. And so we looked at privacy as well. And of course, you can try to combine both into the same setting, meaning have secure and private computation. So I'm going to spend most of my time on the first part, which is the fault-tolerant optimization or secure optimization, and briefly come to privacy. And then if there is time at the end, I will take a brief detour and tell you how I came to work on any of these questions at all, because, you know, as my introduction said, I worked on mobile computing and things like that for a long time, 20 years. So how do you get from mobile computing to this problem? And there is a logical way to arrive here, actually. If I had time, I'll talk about it. So we saw this problem earlier, but now suppose that one of us is compromised. Let's say this is number 3 is me at the bottom of the screen, and I'm the bad guy. And what I want to do is to drag everybody for dinner to wherever I happen to be. I don't want to go anywhere else. I want you to come there. And remember what we're trying to minimize. We're trying to minimize the summation of all the cost functions, sigma fi of x. What if this agent 3 pretends to have a cost function that has very low cost where I'm agent 3 now, right? So my cost is very low where I am. That's what I'm claiming. And it's very high everywhere else. So if you try to minimize the summation of all the costs, then of course you're going to pick a location that's very close to where I am. And by misbehaving, I can control the outcome of the computation quite a bit. And same thing in machine learning as well. So if you're training a neural network, for example, in a distributed way, by tampering with the information being communicated, the fault agent can control the outcome of the training, in this case, the model parameters for the neural network. So obviously that's not good. And question then is, what would you do? Actually, this slide just illustrates why things might go bad. I have said this already earlier, but this is the algorithm we saw previously. And like I said, if the bad agent uploads bad gradients, then the server, because it just performs a summation here of all the gradients, obviously the outcome may be potentially bad. And what you probably want to do is not have the server just use all the gradients as they arrive. Maybe we should clean them up. So the server receives all these gradients. Maybe the server should look at the gradients and say, you know, maybe this gradient looks bad, or this gradient looks good, or maybe do something different, something more intelligent, or less intelligent actually, but somehow clean up what it is receiving before taking the step. And that's in fact what we do in all of our algorithms. The question of course remains is, what does that cleaning up mean? How do you filter these gradients? And what is the outcome? What does that give you? But before we go there, The question is, what do we even mean by fault tolerance? So we know we are doing a distributed computation. We want to protect ourselves from bad guys, but what does it mean to protect ourselves? So we have been working on this since 2015 or thereabout. And when we started working on this, the problem wasn't quite defined. And so we decided that this is the right goal, somewhat arbitrarily. And so we said, what we really want to do is that given that there are some good agents and some bad agents, what I want to do is to minimize the cost of just the good agents. So what I really want to do is to find the argument that minimizes the total cost over just the good guys. The agent I belongs to set G, where G is a set of good or non-faulty or well-behaved agents. The only catch is that if I'm one of the agents in the system, I actually don't know who the other agents are that are faulty. These agents don't necessarily come with labels. I cannot look at their functions and tell that the function is bad. So in some sense, I'm making an assumption of sort of a worst case adversary who happens to be smart enough to not behave badly in obvious ways. If somebody behaves badly, such as by sending messages that are, maybe just omitting messages in a synchronous system, then I know that the adversary is bad, for example. Or he can send messages that are formatted badly, and I can tell the adversary is bad. So let's eliminate all that. We are not going to try to identify the bad adversary at all in our work, and yet try to filter their negative impact. So, like I said, this is the goal. Find the argument that minimizes the summation of the cost over all the good guys. The question is that actually possible? And the answer is that it depends, as many things in life. But the question is, what does it depend on? It depends on the functions themselves. Remember that we have n agents, and each of them has its own cost functions. And depending on the kind of cost functions they have, it turns out that either we can solve this problem or we cannot solve this problem. And there's a spectrum of these cost functions. On the one end, on the left here, the functions are completely independent, in the sense that even if you knew the cost functions of all the agents but one agent, you could not learn anything about that one missing function. There is no correlation that I can assume between the functions I know and the functions I don't know. At the other extreme, you have some notion of redundancy in these cost functions, which I haven't defined, but we have enough redundancy, whatever that enough means in quotes. If you do have enough redundancy, then in fact, you can solve this problem that we set out, which is to say, compute the minimum of over just the good guys without knowing who the good guys are. And then there is in between that maybe the functions are not entirely independent, but and they also don't have this enough redundancy. What do we do? At this extreme on the right, there is a trivial example that to illustrate that it is indeed possible to have enough redundancy. Imagine the situation of this example for dinner, where we all happen to be together right now in a conference room physically. And then we are heading out for dinner later. We are all starting in the same location. We want to go to the same location. Our cost functions will indeed be identical. Then the problem is trivial, isn't it? Each of us can solve our own cost function. We know our own cost function. We minimize our own cost function and go there for dinner. And we'll all end up in the same place because our cost functions happen to be identical. Now, that's an extreme form of redundancy, which in fact happens to be true in some settings, but you don't need that extreme redundancy for this problem to be solvable. So in the remaining 15 minutes or so that I will speak on fault tolerance, I'll give you just a couple of simple ideas. So let's talk about independent functions first, just to point out that you cannot solve the problem with independent functions because the function of one agent tells you nothing about the function of another agent. So here's an example of 3 agents where they're trying to meet on this street. So the argument is a scalar. So X is in general a vector. In this case, X is a scalar, which is just a location on the street. And these agents, let's call them ABC. They happen to be at locations ABC to begin with, and they want to meet. Suppose I am this agent A on the very left. And what I want to do is to find this location for meeting while allowing for the possibility of one bad agent. So let's call the number of agents in the system n, so n equal to 3. And I want to tolerate t faulty agents. In this example, t equal to 1. So if I'm agent A, I have to allow for C being faulty. So if C is faulty, what we want to minimize is the cost of A and B, in which case we end up meeting, or we should meet where this green arrow is pointing. On the other hand, it could be that B is faulty and C is fault-free. Then you want to meet where this other arrow is pointing. Now, me being agent A, I actually don't know which of them is faulty, and yet I had to decide whether to go to that other location here or here. And you can never decide correctly, because no matter where you decide to go, you could turn out to be wrong. So this is a trivial example to point out that in general, when the functions are independent, it's easy to show that you cannot actually solve this problem at all. So question then is, what do you do? If you cannot solve the problem, you cannot declare defeat, because you still have to go for dinner. So in the case of independent functions, we can try to approximate this goal that we have at the top of computing the minimum over just the good guys. Before I tell you how you might approximate the goal, actually I want to get to the other extreme and talk about the redundant case, and we'll come back to the independent functions and approximations briefly yet again. So let's take the case of redundancy. And if you have enough redundancy, we can in fact achieve this particular goal. So here is an example of redundancy. Again, we have n agents, of which up to t can be bad or Byzantine faulty. And what you want to minimize then is that the cost over just the good guys, like we said earlier. And here is the redundancy that I'm going to demand. So let me just read this and I'll try to explain this. So remember that we actually have at least n minus t good agents. And what we want to minimize is the cost of all the good agents, all of them. There could be n minus t, there could be n, but whatever number that happens to be. Suppose you minimize the cost of all the good agents, and suppose that cost is minimized at an argument, let's call it x star. So x star is the location where the cost of all the good agents is minimized. And the number of good agents is at least n minus t. What I demand is that the cost of any n minus 2t agents, which is now smaller number than all the agents, all the good agents, what I demand is that the cost of any n minus 2t good agents be also minimized at x star. Okay, so I'm asking for much more than what we really want to achieve, right? We just want to compute the x star, that is the minimum of all the good guys. And what I'm asking that this be true, that the cost of any n minus 2t agents be also minimized at same x star. And this is what I mean by redundancy here. If you allow me this particular property, then in fact I can solve this problem, meaning I can actually compute x star without knowing which agents are fault-free. And the algorithm that achieves the correct outcome is the one we saw earlier with the filtering step. So what is the algorithm we saw earlier? The server maintains an estimate xk. It sends the estimate to all the agents. It's an iterative algorithm. The server sends the estimate xk to all the agents. Agents upload gradients to the server. The faulty agents can send bogus gradients. And then the server applies this step, which is to say xk plus 1 equal to xk minus lambda times the so-called filter gradient. And I have to yet tell you what the filter gradient means, and I'm going to tell you next. So here is a filter that works. There are many such filters that have been proposed over the years now. But this is a very simple filter in a way, computationally. So here are three gradients that in our example. What the server is going to do is to compute the norm of the gradient. Norm is just the length of the vector. So each vector has a length and a direction, and C is going to compute just the norm. I should have drawn two bars here instead of one for the norm. But let's say these are the norms of the three vectors, 1, 3, and 2. And what this particular filter does is to take the largest t vectors, the longest three vectors, t vectors. In this case, t equal to 1. So we only look at one vector, which is number 2, and make it shorter. How short? We make it as short as the t plus 1th longest vector, which is in this case length 2. How do you make it shorter? Just multiply it by 2/3. And so all we have done is to keep the directions of all the vectors the same. Some of them may be faulty, they're still pointing in the wrong directions. But we scale some of them, the longest t of them, and then we add them up, and that's what I mean by filter gradient for this particular kind of filter. And for other filters that we have proposed and others have proposed, the computation tends to be different. But in the end, we do this step. Now, under the redundancy condition, I assume, and I had to make a few more technical assumptions that I won't spell out here, this particular filter will work correctly, in the sense that if you run the algorithm, the iterative algorithm, long enough, that xk will converge in the time limit to the true minimum over all the good cost functions, without knowing which cost functions are good or which agents are good and which agents are faulty. Now, this condition I stated here seems a bit too stringent. Turns out that not only is it sufficient, it is necessary. So if you violate this condition, then I cannot guarantee that the algorithm will compute X star correctly. So in general, this condition may not actually hold true. So I'll come and I'll talk about that in a minute. What happens if the condition is not true, or what can you do? But let's look at one more example, that of machine learning, where this redundancy can happen quite naturally because the data that is available to different agents may be highly correlated. In fact, in extreme settings of server-based machine learning, it's often assumed that all the agents, they're often called the workers, all the workers have access to the same data set. And often this is done in the context of stochastic optimization, stochastic learning. In that setting, we assume that the agents or the workers are drawing gradients from identical distribution, IID distributions. And when we say the distribution IID, we are actually saying that the agents are basically identical in an expected sense. So this notion of redundancy is not completely contrived. It happens naturally in many settings. In the context of sensing, where you may have sensors that are trying to estimate the temperature in the room or looking for an object, such as an intruder, as well, you have a lot of redundancy because you have more sensors than minimally required. And if you represent those problems in the form of cost minimization, they exhibit redundancy as well. So that was just very briefly about the redundant case. Now let's come back to the setting where we may not have redundancy that is enough, or we may not have any redundancy at all, meaning that the cost functions might be independent. So let's take the independent case first. So if you have independent functions where no function tells you about anything about any other function, what do? You cannot solve the problem we set out to solve. How do you approximate it? It turns out there are multiple ways of approximating things. I'll discuss one of them. So remember, our ideal goal is to compute the argmin of sigma fi of x over all I belonging to set G, where G is a set of good nodes. This is exactly the same as sigma 1, the argmin of sigma 1 over G of fix. I just multiplied by each cost function by a constant. The argument that minimizes the cost function doesn't really change. But this cost function can be viewed as a weighted average of all the individual cost functions of the good nodes, where the weights happen to be equal. The weights happen to be uniform. So it's a uniformly weighted average of all the good cost functions. And I just showed you a very simple example of 3 agents that argued that you cannot actually compute the argmin of the uniformly weighted average of cost functions. So the question then is, can you do something weaker? Can you compute the argmin of a non-uniformly weighted average of just the good functions? I don't want to assign any weight to the bad functions in my outcome, but can you give me at least a non-uniformly weighted average of the good function? The answer happens to be yes. So I'm just going to state the result. We won't discuss the algorithm. The result I'm stating is for the case of argument x that is scalar, but there exists analogous result for vector arguments. So what can you do? This is what you can achieve. I can compute an output, let's call it x hat, which may not be equal to x star. However, the x hat will be a minimum of a non-uniformly weighted average of the good cost function. So what is non-uniformly weighted average? Imagine that instead of 1 over G here, I'm multiplying Fi by alpha I. So alpha I is a weight, a non-negative weight assigned to agent I. It's just that the alphas may not be equal anymore. But the faulty guys will get no weight in my computation. However, as a cost of tolerating faulty agents, some of the good agents might get the weight of 0. So if I'm good agent number 1, it may so happen that I might end up with alpha 1 equal to 0. What that means in reality is, in practice, is that my opinion is being ignored. So for example, if you're going for dinner, and if you happen to give me the weight of 0, it's like saying that my opinion gets no weight at all in the final outcome. But that may happen. If I'm tolerating T good agents, it may so happen that T bad agents may get the weight of 0. However, the remaining good agents, so imagine that we actually have T bad agents, and then T good agents might be sacrificed, and what remains are n-2 T agents now, good agents. We can guarantee that they get roughly uniform weight. So remember what we set out to do. The ideal goal was to make sure that all the alpha i's are identical. And that's impossible to guarantee when the functions are independent. But what we can guarantee is this particular outcome, that I may sacrifice up to T good agents, but everybody else I get roughly uniform weight within a factor of 2 of the uniform weight. It turns out that this is also a lower bound, meaning that no algorithm can circumvent this first result, which is to say that if you try to tolerate 2 good T bad guys, T good guys might be sacrificed. There exists no algorithm that can avoid this. And so in a way, the result I'm stating here is pretty close to what you can get. So instead of getting a uniform vector, I'm getting a non-uniform vector, which is as close to the uniform vector as we can possibly be under the circumstances. So this is one way to approximate things. It turns out this approximation degrades very rapidly as you increase the dimension of X. So if your functions remain independent, so if you have no constraints on the choice of the functions, and if your argument X is D-dimensional, so D could be 2, if you're in a plane, it could be 3. In case of neural networks, the dimension could be millions. The number of good agents you sacrifice scales linearly with number of faulty agents, and it also scales linearly with the dimension. Actually, it's D times T. You have to sacrifice D times T agents for dimension D and T faulty agents. And that's very large when D is large. So this is a very unsatisfactory result in the event when the functions are independent. However, this is unavoidable. It turns out that this approximation gets rapidly, it improves very quickly if the functions have some correlation, some dependence. And in practice, it would be rare to have functions that are completely independent. In fact, it's not surprising to see a lot of correlation between functions, let's say in a machine learning setting, for example. And so there is bad news and good news both on this slide. As far as the algorithm that achieves this goal, it looks structurally exactly the same that I showed you before. You can use the same filter or you can use a different filter to achieve the same goal. Now, what I said in passing is that there are many different filters that have been proposed here. And the question then is, why do I have multiple filters? I only showed you one of them, by the way. One of the other filters that's been used for the scalar case, meaning when X is just a single real number, is one that many of you have seen in the work on Byzantine consensus, the so-called trimmed mean filter, where you throw out the outliers and average the rest. That filter also works if you make the right technical assumptions. So there are many of these filters that work within quotes, but they differ in their complexity, the computational complexity, and they also differ in the additional, the so-called technical assumptions you have to make to achieve the right outcome. In general, the simpler the filter, the more assumptions, more additional assumptions we'll have to make for the things to work out. What I won't discuss in detail for lack of time today are other ways of approximating. But just briefly, if you recall, I stated this redundancy condition earlier that said that any n-2 t-cost functions have to be minimized at x star as well, but x star was the minimum of the summation of costs over all the good guys. That was a very strong condition I imposed. Now, you can weaken that condition a bit and then guarantee results that look something of the form in the second line here. This is stated somewhat imprecisely, but roughly speaking, what we can guarantee is that I cannot produce X star anymore because I don't have that redundancy I demanded previously, but I can produce an output, let's call it X hat, that is within some bound epsilon of the true X star that I'm trying to produce. And the larger the epsilon you're willing to tolerate, the less redundancy you need effectively. So these results exist. If you're interested, please refer to some of our other work. But what I want to do now is spend a few minutes, maybe 10 minutes talking about privacy, and then I'll leave 10, 15 minutes for questions if there are any. So what we discussed so far is fault tolerance, where the agents are actually misbehaving and providing bad information. In this dual problem, we don't have anybody sending anything bad, but the adversary may be trying to learn my cost function. So for example, if I'm agent number 1 and we are trying to meet for dinner, I may not want you to know that I am sitting in some bar right now working there in the middle of the day, right? So I want to hide my location. And yet we want to compute this true global minimum that depends on my current location through my cost function. So I want to protect my data, my cost function, and yet solve this distributed objective. So this is not a new problem, right? People have been working on multi-party privacy preserving computations for a long time. But here we are exploiting the structure of the problem to propose a slightly different solution. So why is the privacy compromised anyhow? Remember, these agents are supplying gradients to the server. So suppose my cost function is just a straight line. Suppose it is X is a real number and my cost function is 2X plus 1, right? It's a very simple cost function. Then my gradient is just a constant 2. The moment I supply the gradient to the server knows my cost function looks like something like 2X plus a constant. So by receiving enough gradients from the agent, the server can infer a polynomial cost function up to a constant. And the more the server knows, the more he can learn about the cost functions. And we don't want that. So there are many ways of potentially solving this problem. One can use cryptographic techniques, for example. One can use the generic multi-party computation techniques and apply it to this particular setting. But here is a somewhat different solution that combines at least the intuition from secret sharing and differential privacy, something we call the cancelable noise, at least intuitively speaking. So here is an idea. So for our solution to be useful or usable, we need to have multiple servers. We are preventing the servers from learning the cost functions. And in this setting, we need more than one server, and the assumption that all the servers are not trying to compromise our data. So in this example, there are 2 servers. Maybe server 1 is the adversarial server. I don't want him to learn my data. Server 2 is a good guy. They're not trying to compromise our privacy at all. And so the assumption is that there are multiple servers, all of which are not adversarial. And these agents will communicate with multiple servers. You can extend this to 3, 4, 5 servers, and the agents can talk to all of them or some subset of them. So you can make this server client network much more general. The server to server graph is a communication graph as well. It can be complete, doesn't have to be complete. But in the simplest case, this is a topology where we can use 2 servers and 3 agents. And the agents are going to upload gradients to the servers, as we saw in the algorithm before, right? The servers will send estimates to the agents. Agents will compute their own gradient and upload to the servers. So that remains unchanged, with one difference. Each agent now, when it uploads the gradients to different servers, doesn't send the true gradient to the server, but adds some noise to the gradients that are uploaded to the servers. And the noise is added such that the noise will cancel over time and space. By time, I mean, I might add a +1 in current iteration and -1 in the next iteration. That's what time means. And over space means I'm adding noise to different servers. So when I add noise sense to all the servers over time, over some bounded interval, that cancels out. And each agent does the same thing symmetrically. And in our original algorithm, we only had 1 server, so that was easy. But now the servers are actually multiple ones, and we want them to also be able to arrive at the same decision, meaning the same output. And so they have to perform something called a consensus. I'm sorry, I'm going back here. They had to perform something called a consensus step every once in a while, where they basically exchange each other's estimate and then compute a new estimate as a weighted average of each of those estimates. The details are not terribly important, but this kind of structure gives us privacy in the sense that I can tolerate a subset of the servers being adversarial and still perform this distributed optimization correctly, meaning solve my original problem of minimizing the cost, aggregate cost over all the good agents. And just to explain what's really happening, in a little bit more intuition behind what's happening. Here I explain in my slide that I'm uploading gradients and adding noise and things like that. This is a different view of what's happening. So let's say, again, we have 3 agents, agents 1, 2, and 3. But now agent 1 actually simulates two new agents. Let's call them agents 1, 1, 1, 2, 11, and 12. And each of these little agents now have their own cost functions. This agent 1, 1 has cost function P11 of X, and agent 2, or rather 1, 2 has cost function P12 of X. And these cost functions are simulated. The agents are themselves simulated. The cost functions are chosen such that they add up to the original cost function of agent 1, F1 of X. And agent 2 and 3 will do the same thing. They will split their cost function such that if you add the cost functions back, you get the original cost function F2 or F3. And now you have a system with 6 agents, each of them having its own cost function. Nobody's adding noise to gradients or anything like that. And the only new thing compared to my original architecture with multiple agents and one server is that I have 2 servers, but they will perform a consensus step that I have not spelled out, but it's just something where they agree with each other what the new estimate is. So this structure is essentially identical to my original solution without any noise in the gradient. And the only difference, which I did not articulate at all to begin with, in a lot of the literature on these kinds of distributed optimization solutions, the assumption being made is that function F1 of X is convex. Now, if I split F1 of X into 2 cost functions, P11 and P12, I might get P11 and P12 that are not convex, and yet they add up to a cost function that is convex, because that's by construction. So what that means then is that even though the individual cost functions may not be non-convex, the sum over all these 6 cost functions still remains convex. And turns out that under that condition, this algorithm still converges to the true minimum of all the cost functions. So that's a slight sort of technical contribution, if there is one, to achieve privacy through these means. Now, we are not explicitly splitting the function this way. We are doing it implicitly by adding noise in the gradients. However, one can design explicit algorithms like this too in settings where the cost functions are compact, maybe written down as a formula. So, like I said earlier, we can get some notion of privacy. I'm putting that in double quotes because I have not even defined what I mean by privacy really. If at least one server is non-adversarial in this case, but in general, if a subset of the servers is non-adversarial. So just to summarize the technical part of this talk, we introduced the problem of distributed optimization, and machine learning or distributed learning is just a special case of distributed optimization where the cost function happens to be, let's say, the loss function for neural network training. And we looked at fault-tolerant algorithms that tolerate bad agents. And the solutions I introduced, they all tend to use the so-called gradient filters. And in case of privacy, in both cases where I discussed server-based architectures, for privacy, we use cancelable noise. Now for privacy, we have solutions that apply to this setting of peer-to-peer network as well. For fault tolerance, we have very few solutions, or rather very few solutions with good quality outcomes for the peer-to-peer setting. So the fault-tolerant optimization problem for the peer-to-peer setting is mostly still open. So like I said earlier, I want to tell you briefly how I came here, because for some of you, that may be the most interesting part or most useful part of the talk if you don't care about optimization problem. So my PhD, this is 90s, early 90s, was in fault-tolerant computing, but for the next 20 odd years, I worked on wireless networks and mobile computing, and I was doing more applied work, building systems that look like this. You don't need to know what the slide is, but this has relevance to how I came to work on distributed machine learning. So I was working for a long time on wireless networks, like I said, And one of my colleagues back at the University of Illinois, where I worked before I came to Georgetown, he was implementing something called the average consensus algorithm in a peer-to-peer manner on a wireless network to control a network of power generators. And average consensus just means computing average over a bunch of numbers, where each agent starts with a number using a very cute, distributed, completely peer-to-peer algorithm, very local algorithm. And the algorithm wasn't working correctly because his network was lossy. It's a wireless network. It will lose packets once in a while. And the algorithm he had was synchronous. And one way to fix wireless transmissions reliability is by just retransmitting the messages, but then that makes the communication asynchronous, and the synchronous algorithm wouldn't work correctly. So he came to me saying, can I give him a wireless network that would let him build a synchronous algorithm that was lossless? And I said, that's something I cannot really do. But then I started talking about what the problem was that he was working on. Then he explained to me it was average consensus, and this is the algorithm that he was trying to implement. So as I learned what he was trying to do, I learned a lot of the tools he was using, but we also ended up with a solution to the average consensus problem that worked correctly despite the links being lossy. And so even though we could not make the wireless network lossless, we could actually get the algorithm, a new algorithm, to work correctly on a lossy network. And this was my introduction to the problem of average consensus. It turns out average consensus is just a special case of optimization. So if you're agent I and you have value AI, average consensus wants to compute the average of sigma, average over all the AIs, which is just sigma AI divided by n, the number of agents. But that's equal to argument, the argument that minimizes sigma x minus AI squared for the case where the arguments are real numbers, but this extends to vectors as well. So once I understood average consensus, for me, the natural question was, what about Byzantine average consensus? What does it mean to compute averages when there are some agents that are Byzantine faulty? But then when we quickly made the connection to optimization, we said, why not work on optimization instead of average, because that's much more general. And then once you start thinking about optimization, learning is not that far. And this started with average consensus. What I do today has nothing to do with what I was doing then on that one paper, but that effect, that has led to everything I have done for the last 5 years. This is a slide that I project when I'm in a physical room with people and take a poll. We won't do it today. But on this slide, what you see are names on the left of the red arrow, on the right of the red arrow. And for people in this audience, some of papers on the right-hand side look familiar, right? Peace, Shostak, Lamport, you probably know the Byzantine consensus paper, and others, you know the FLP result probably. The names on the right are very familiar to people who work on control theory, decentralized optimization. Usually audiences that know the names on the left have no idea who these people are on the right. If the people who know the names on the left, the only reason they know Lamport is because he wrote that blue book on LaTeX. They have no idea that Lamport is a Turing Award winner, has worked on consensus, any of that, and vice versa. It turns out these two communities are both working on very similar problems. In fact, they're both working on consensus. The number of papers on consensus in the community on the left-hand side is perhaps larger than the number of papers on consensus in distributed computing, because it's a much larger community. But their notions of consensus are slightly different. Whereas in our setting in distributed computing, the very first paper on consensus was fault-tolerant consensus, because faulty consensus is almost trivial. We almost always assume actually not almost, always assume scalar inputs. In fact, they're very often are typically discrete because we're doing consensus in the setting of computer systems, agreeing on some commands issued to a server. Most of the literature in consensus tends to be complete graphs, and when they're not complete, they're undirected. And of course, we do synchronous consensus and asynchronous as well. But the synchronous algorithms tend to be finite time, meaning that they terminate within some number of iterations. And the algorithms tend to be global in the sense that we tend to assume that the network is known to the entities performing the algorithm. In the literature on decentralized control and distributed optimization, for many years, for 35 years, the work assumed no faults, the agents behaved correctly. The arguments were almost always vectors, because if you're a control theorist, the vector state, the X is actually the state of your system that you're trying to control, and the state is typically a vector state. There are many things you're trying, many control inputs. The network is typically assumed to be undirected, incomplete graph, and often a directed graph. And even for synchronous systems, the algorithms they study tend to be convergent algorithms, meaning they only get to the exact true solution in time limit as t goes to infinity. And the algorithms in the peer-to-peer setting tend to be very local, where I only talk to my neighbors, and I usually don't even need to know how many agents are in the system. I don't need to know what the topology is. And starting with that one interaction many years ago, I don't even remember anymore how many, probably 8, 9 years ago, everything I've done since then is impacted by that interaction. And for example, we've been writing papers on fault-tolerant consensus with vector inputs. So it marries faults on the left with vector inputs on the right. We have consensus algorithms on incomplete graphs that are directed graphs. And very surprisingly, none of these results were known in distributed computing, right? We have known that 2f+1 connectivity is required for Byzantine consensus. In undirected graphs, we have known this for close to 40 years. But we did not know what the condition was on directed graphs, mostly probably because nobody looked at it. And the problem is far more difficult than the undirected graph case. The point I'm really trying to make is that the takeaway really is not that we did all this, but takeaway is that the reason all of this came about is because I was talking to somebody who was nothing like me. This particular colleague worked in power system and had background in distributed control and optimization, of which I knew nothing at all when I started working on him. And he knew nothing about our community either. But by talking to somebody that far away, I found something that has a mutual sort of overlap in fact, the problems, right? The consensus problem we both worked on. And yet there were many things at the intersection of these two communities that nobody had addressed. So if you're a student and even young faculty, talk to people who are outside your area, because that's where you might learn something far more useful. So with that, let me acknowledge my colleagues. These are my students and postdoc. Not everybody is listed here, but these people I worked with most closely. And the work is funded by many agencies, including NSF and ARO. So with that, thank you. Thanks for inviting me for this keynote.
Thanks, Nitin. This is inspiring and love the conclusion. And it's actually interesting. It is crossing boundaries. I will open the room for questions. If you have questions, raise your hand, or just unmute yourself. Ask on Zoom, ask on Slack. We will find a way to ask a question. Borzo.
Nitin, thank you so much for the talk. I'm wondering if the same type of concepts can be applied to neural networks.
Yeah, so in general, the cost functions may not be convex. For example, if your loss function is convex, first of all, then this applies. So what I did not say, because we didn't have the time, is all the theoretical analysis, at least in our case, assume the functions are convex, which is to say they have a minimum. If it is strongly convex, it has a unique minimum, but it has a minimum. You don't have local minimum, only a global minimum. But your cost functions may not be convex; they may be non-convex. And although in our work we haven't studied non-convex functions, some people have for the non-fault tolerant case anyway. And many of these algorithms will converge to the local minimum. You cannot give global minimum, but they'll get to local minimum. And in machine learning, there is other literature, which has nothing to do with what we're discussing here today, that shows that under some condition, all the local minima are also global minima, meaning the local minimum are performed well for a reason. It's not an accident. So yeah, in practice, a lot of this applies, but the theory doesn't necessarily give you that conclusion.
Thank you.
Meaning we don't have theoretical results for non-convex function.
The ball.
Hi.
Yeah.
I had a question. Have you considered combining the fault tolerance and privacy techniques together? And if so, would those work in conjunction or?
So we did look at this many years ago. And one of the students at Shripad, whose picture you saw, he was working on this problem for a few months. I mean, first of all, certainly you can try to combine the two. Clearly, they're working against each other because privacy, you're trying to make things noisy, and fault tolerance is trying to throw out noisy things. So that's the trade-off we're trying to analyze. It gets a bit messy, and so we never published it. But last year, or was it even this year, there is a paper from EPFL, which is co-authored by Rashid Garoui, I think, and one of my postdocs who is now working in Rashid's group, that appeared at, I believe, at PORC this year, which also tries to look at privacy and security together in a particular setting. I mean, there are many different settings you can ask the question. But yeah, there is a tension between the two. Not too many results that I can say. In fact, that's the only paper that's been written. Our work, we never published it.
Thank you.
Yeah.
Other question. I have one. I was thinking the role of multi-layer learning, so and adversary learning in this. So so when you think about, I'm not an expert, but I've been talking with faculties that were working on distributed learning, and this idea of filtering possibly faulty results. One way we were thinking of approaching it, which I think approximates to your the part where you talk about redundancy, is how about we, instead of sending all my parameters to a central server, how about we build a hierarchy, right? So so each location by itself becomes a system where you have multiple agents that provide information, and the idea is that the machine learning process itself will kind of filter out noise. Yeah. Now, we never thought about somebody that intentionally is trying to push the data so that in a Byzantine behavior, let's say. So for that, there are solutions on adversary machine learning, right? So that's where you're building a model that fights another model, so it's fascinating thinking about all these things together. I was wondering. So one of the questions I had is, how do you, if you're not having so many agents that can help you with probably what you call redundancy, how do you identify that somebody is intentionally misbehaving, and is that so much related to the application? In the examples that you have made, you're trying to learn what happened in a geographic location, and you have an agent that provides that. I know that behind that agent, there can be a lot. But you can think about other machine learning approaches in which even if somebody is providing an information that is not accurate, is not providing anything, it's still a best effort approach, right? So you're not like making a big issue. It's not like breaking consensus where there are money over it. And I understand applications are very different. So I was wondering, what is the role of the final applications where you're targeting, and yeah.
So in our work, we somewhat artificially say that we will not try to identify bad agents, because we wanted to look at what we can do without identifying the bad agents. But in general, you can try to do that. So in coding theory, for example, you can do detection and correction. So in our case, we are sort of doing only the correction, meaning we don't even try to say this bit, who is bad. We just want to get the right outcome. But in general, particularly in machine learning, one can try to detect bad agents as well, meaning maybe you cannot identify the bad agents precisely, but maybe with high probability you can be right. So you may have false positive and false negative, but at least by and large, you're doing a good job. So one solution that some people have investigated is where, remember, the agents have all the data, and agents are performing the computation. But you can imagine that the server perhaps have access to a small subset of the data, or a small sample of the data. And what the server can do is, when it gets the gradients from the clients, the server can also compute its own gradient. Mm-hmm. And of course, the server only has approximate gradient because it doesn't have everything. But the server can potentially use the knowledge it has and what it receives from the clients and say, okay, this looks too different to be true, right? And so there have been solutions of that sort that have been proposed. For example, to make this much more precise, the clients may be using a large batch size. So let's say all the clients are IID, they have access to the same data. And the reason you have all these workers is not because they have different data, but because you want to get parallelism. So this is more a parallel setting, not distributed. But the workers may be using a large batch size, so they get gradients with small variance. The server may be using a small batch size, gradient with large variance. But yeah, people compare, they have proposed keys where they compare the gradients and say, okay, they look too different. Maybe the client is faulty here, right? Now, this is not foolproof, but improves are not compared to not doing anything at all. And then one can apply the kinds of filters we have on top of those kinds of schemes as well. So yes, application dependence, certainly, if you know something about the application, then you can add other bells and whistles as well.
Have you looked into specific applications or where knowledge about the application can help?
So we have applied, these algorithms to machine learning data sets, but we haven't changed the algorithms to apply to machine learning. We just use the same algorithms. But we have demonstrated on data sets, machine learning data sets, how these algorithms behave.
Thanks. So our time is over. If there is any last minute question, we'll be happy to take it. Otherwise, thank you, Nitin. This was inspiring. And I hope everybody enjoys it from the recording that will be online. Thanks again. Big applause from the whole community. And please stay on. Next session start in 15 minutes.